Okay, great. Okay, welcome everybody to another MCRN Colloquium. Today we're very lucky to have two speakers. One is Professor Blake Barker from Brigham Young University. Many of you know Blake. He's been an active member of MCRN for a while now. He got his PhD in 2014 at Indiana University and then did a NSF postdoctoral fellowship at Brown under the mentorship of Bjorn Sandstred. I probably said that wrong. But now he's been an assistant professor of mathematics at Brigham Young University since 2016, with a large interest in traveling waves. I think recently he's been also advising this MATH F.I.R.E group, which we'll hear about, of which Lydia Tolman is a master's student and a member of that group, also working on F.I.R.E, which is certainly more and more important these days. So with that, please, Blake, take it away.
All right, thank you for that introduction and the opportunity to speak. So today I'm highlighting some of the research that students here at BYU have been doing in our Math Wildfire group. This is a group that started with Emily Evans as a co-founder, also a professor here at BYU, and now that I continue to co-mentor with Mark Allen, a professor here at BYU. So this started back in 2018. We had this really large fire here close to the university, just a little bit south in the valley, and it came within about a quarter of a mile of the city over there, and it burned a huge swath of area. It was quite an intense fire. It burned with such intensity that it didn't leave a lot of vegetation behind, and so this was a experience. It was a year that we were looking for projects, and it had an influence on us and what we wanted to do. So we developed the MATH F.I.R.E group, FIRE standing for Fire and Industry Research Experience. So one of the first things we did with a group of students was work on identifying the perimeter of wildfires. And this is an important and difficult task because you have things like smoke that get in the way of seeing where the fire is burning. You also have, in your images, you have quite a bit of noise. And so you look at different channels of light and images, and you try to piece together what the fire looks like. So here on the left is an image. And then here on the right is a picture of what these students identified as the area that had been burned by fire in this image. And they accomplished this by running atmospheric penetration images through a Gaussian Laplace filter. And then they used a threshold from the resulting histogram to say this area has been burned and this area has not been burned. And I will note that if you look at this picture on the left, to our eyes it seems pretty easy to see what's been burned and what's been not. But if you look over here on the right, in the upper right corner, there's a little bit of white indicating a burn area. And then you go back here on the left and you see that it is there. So, and that's something that the first time I completely missed. So this was really great. So this started off the MATH F.I.R.E group, this research that these students did, and they did a really nice job with it. And so then the next thing we did is, one of the students, Tyler Jones, as part of this research effort, developed a agent-based model of wildfire spread, so a stochastic agent-based model, or some people similarly call it a cellular model. And he also used his graph theory skills to look at minimal cuts. So the idea is, let's say there's a wildfire burning, and you've got a wildfire front, and then you've got a building or some other feature that is of significance that you're trying to determine how to prevent the fire from reaching. And he looked at the connectedness of different grid points in the forest to see what point is the fire most likely to go through and reach this building, for example. And using minimal cuts, he identified that. So it has has an application in that regard. And then he incorporated into his model that various kinds of forest will burn at various rates. So that was a really nice project that he did for his master's project. And then about the same time, another student, Andrew, or Drew Johnston, was working on data assimilation and wildfire modeling. So here on the upper left, you can see the Dixie fire that burned in California back in 2021. This was a massive fire that burned for months. And so his goal was to take a model for wildfire spread. He took the model by Mandel and collaborators, which is a partial differential equation that has a fuel term that is incorporated into the model. And what he did is he modified that model so that it would allow you to give various fuels a different burn rate. So basically account for the fuel source in determining the spread of the fire. So he took several different categories for different types of fuel, and then he used machine learning to identify from a satellite image what type of fuel was present. And then he used data assimilation to identify the appropriate parameters to associate with those various types of fuel so that the fire would spread according to those fuel types. And then as a test run, he ran it on this very large fire. Now I will mention that this is an extremely challenging model to, fire to test his model on, to validate his model on, because for one thing, it was burning for months, it was actively fought, and looking at the satellite images, you don't know when the fire stops because there's a fire line put up by the firefighters on the ground, or a plane comes over and dumps retardant on the fire. And so this is a very difficult test that he's using here against his work. I also mentioned that in working with the satellite imagery, you've got satellite imagery of the Earth's surface that's coming from different angles. The Earth has curved. This is a large area that these squares represent in this top right picture. And so you've got to identify what you're seeing in 2D with what's actually occurring in 3D. And for that, Drew used homography. Okay, so here on the bottom right, we look at his results. So now he's tested the wildfire spread versus the actual data. And on the left, when you get new data, new satellite imagery saying where the wildfire perimeter is, he doesn't restart it. And you can see in light pink where his predictions match what the wildfire did. And then you've got areas that he predicted that didn't burn, and areas that in gray, and then areas that did burn that he didn't predict in red. And then here on the right, when the satellite imagery comes in, now this occurred over months, so this difference in time is probably on the order of about a week or so, I believe. But here on the right, you see, okay, when we get new data, we're going to restart our model with that new wildfire perimeter, and then see how it tracks. You can see it does much better, and really does quite well, because until the last couple of frames, it's tracking extremely well. So this was an exceptional thesis, and built on the work of these other students that had been working. So kind of the pattern we have is a master's student or PhD student can work on a thesis or PhD, and then related to that are other problems that are appropriate for undergraduate researchers that contribute, things like finding wildfire perimeters, for example. Okay, so next, after that, if this will advance, there we go. So then the next year, we looked at environmental health of burned forests and smart irrigation. So I mentioned this very large fire that we could see from campus that occurred back in 2018. There is a professor, Professor Ben Abbott at BYU, in the Plant and Wildlife Sciences department, who was researching with his students, his group, the health of the forest after the fire. And so they did this incredible job, just extreme amount of work to collect data from the water. You can think of water as sort of like if you're sick, you can test your blood, right, to see what's causing your sickness. Well, for understanding the health of the forest, you can test the water. And so that's what they were doing. So here you can see all these different water stations in these light kind of blue-green color. And then the wildfire, you can see where it burned, and then some different areas that have to do with the kind of basins of attraction of the water. And so then we had some students that worked with them, helping with statistical analysis. And then also Jimmy Tyler, that is mentioned in both these projects, was doing this for his thesis project. And he also did some stuff with smart irrigation. So we also met through this work another professor in the same department, Professor Neil Hansen, who works on smart irrigation. So this is a really neat research opportunity we had to work with him. So he, with his students, would collect data from fields that were irrigated by farmers. And so you can get the water content and the temperature using these sensors. Now, temperature is pretty cheap to measure, but getting the water content of soil requires machinery that is quite expensive. It also is quite large, and it can get caught in the plow, for example, when the tractor is plowing the field and the farmer's plowing the field. So what he was aiming to do with his group is identify a relationship between temperature and water content to see if one could predict the water content just from temperature. And we were invited to participate in that study. And so our goal there with the students was to first identify if there was a relationship. So we did a lot of work related to data science there. And then we also did some data assimilation. So we used a heat equation for solving the system. So at each location where they would gather the temperature and the water content, they would have 3 sensors at different depths. So what we did with this work, the red here corresponds to the bottom on the right and the top on the left, these sensors at different levels in the soil. And we would measure the temperature and then the water content and then try to estimate it. And the temperature, we were able to, using data assimilation, to get the correct parameters for the heat distribution model. We're able to find what the temperature should be at the middle and match it really well. And this was a lot of work. It was really fun, really exciting. It was a great, again, with both these teams, great people to work with. And in the end, we decided that it wasn't enough information to gather the relationship we needed to effectively predict the relationship that would help avoid these water sensors. So then the next step in our goals to work on wildfire research, and our ultimate goal is to help with the math development and the development of algorithms and things like that that'll help the wildfire fighters have better information or faster information so that they can do their job even better. And they're the true heroes in fighting these wildfires. So so that's our goal. So then we had this wonderful opportunity to work with some researchers at the Missoula Fire Sciences Laboratory, and this is ongoing collaboration. These are the makers of Wind Ninja, which is this really advanced, really incredible program that allows wildfire fighters to model wind. for the purpose of determining where the wildfire might go and help them with their wildfire fighting planning. And so what Wind Ninja does is it takes in a wind field, and then it gives an output. And there are two different solvers that are used in Wind Ninja, at least. One that is a mass solver and one that's a momentum solver. So the mass solver just basically gives you a divergence-free condition. And then the momentum solver solves the Navier-Stokes, the Reynolds average Navier-Stokes equation. And these researchers, at the Missoula Fire Science Laboratory, desired to speed up the computation for the momentum solver and invited us to, through an introduction we obtained, we were invited to work with them in seeking to speed up the code. So then Jane Housley, a student at BYU, for her master's thesis, worked with them and had tremendous success in doing kind of I would call it a feasibility study, and being able to use neural networks to learn the solution operator for this momentum solver and predict from just the input from the mass solver what the solution to the momentum solver should be. The mass solver is very quick. The momentum solver is not as quick, maybe about an order of magnitude slower. And then Lydia Tolman, who will be speaking with us here soon, has continued that work and is now going the next step. So taking the feasibility study and progressing it, she's been working and making great progress on the validation step and moving in football talk, moving the chains forward. So it's been really exciting. And so Lydia is a master's student here. I've just got one more slide I'm going to share, and then I'll turn the time over to her. But it's one of the things I love about working with these students is that they come with all these fantastic backgrounds and skills and things like machine learning and computer programming, and they bring in a lot of expertise that allows us to work on very broad problems that I certainly could not do without their expertise. And then we piece these together for this exciting group work, and of course working with these fabulous collaborators that we've had the opportunity to work with has just made it a really fun experience. There's ongoing work and future plans with, as I mentioned, I co-mentor this group with Mark Allen. He has students working on the spread of wildfire in pine needles and topology and fire spread. With Dr. Jared Whitehead here at BYU, we received an X-Tripods grant to work with Nan Chen at Wisconsin on data assimilation, and as part of that data assimilation with regards to wildfire. And then students currently in our group are working on integrating machine learning into validated solvers so that we can speed up computations but still maintain the methods that have been validated and are currently in use in various applications. We've been looking into adaptive mesh DA and the exciting work going on by people in that area and how it could apply to wildfire. And then finally, I'd like to mention that we're grateful for the funding for X-Tripods, but also for the funding for the broader community in wildfire. I see this as a really important problem, these wildfire problems, for a number of reasons. One is that it has to do with the environment. It's part of the carbon cycle. Of course, it has to do with the safety of our communities. We know that in recent years, many communities have had devastation from wildfires. Whole cities burned down. The cost is in the billions. Lives are lost. So certainly there's that aspect. The smoke from wildfires is bad for our health and has a significant impact on us. And then also, I'd mention that it's a matter of national security as well, to be able to effectively fight wildfires that can occur. And so certainly I'm grateful to the past and current leaders of our country who have dedicated funding to these wildfires so that we can can have good national security and be the best America possible. With that, I would like to turn the time over to Lydia for her part. So let me stop sharing. Oh dear. How do I stop sharing?
In the top right, if you go back. Yeah.
Oh, there we go.
And perfect. Are you able to see that all right?
Yes.
Looks good.
Perfect. Yeah, thank you, Dr. Barker. And so I'm going to be talking a lot about the work inspired by Jane Housley's thesis work. So a lot of this can be attributed to her. So big shout out there. And then also wanted to shout out the Missoula Fire Lab as well as Dr. Barker. So I'm going to be talking about improving efficiency of wind flow modeling for wildfire applications. So just an outline, I'm going to go over some of the background information, and then two different methods that we have explored to model this, how wind flow affects wildfire spread, which are the parameterization method and the neural network, and then some of the results from those. So Dr. Barker mentioned this Wind Ninja solver, that is a tool that is used to kind of model how wind flow over a terrain is able to um, affect wildfire spread. And this is what like the output of that would look like. This is a actual site in Idaho, and the arrows are the wind direction as well as the color of the arrows representing the speed, as I believe. And then Dr. Barker also mentioned these two Wind Ninja solvers, this mass conserving solver and then the CFD solver. The mass conserving solver right now is a very fast way of trying to model this wind, but it is not nearly as accurate as the CFD solver, which is incredibly accurate but much slower. And so the goal with this research is to find a solution that is both fast and accurate, because when you're dealing with wildfires, you want to deal with them quickly. So the mass conserving solver, the motivation behind that one is solving this equation that uses the idea that if wind flow goes in, it must also come out, and it uses the finite element method. And it tends to smooth out some of the finer wind turbulence, which is why we are able to see failure behind obstacles in what we call cavity zones, which I will explain a little bit later. But it is a much faster equation to solve than the Navier-Stokes equations that Dr. Barker mentioned. This is a complex equations that are able to capture a lot of variations in wind and how that may affect the fire. This is considered the gold standard for modeling wildfire spread or wind spread. However, it does have a very high computational cost because solving these PDEs is just a very difficult thing to do. So this is kind of an example of the problems that we are running into with the mass solver. When wind is going and it hits an obstacle, there's going to be a zone in which it kind of circles back into itself, which the mass solver tends to look over and doesn't quite get, because there are a lot of nuances in how the wind acts in this area. So this is an example of one of those cavity zones. On the left, we have the mass conserving solver output, and then we have the CFD solver. As you see, the mass conserving solver, the arrows keep going in the same direction, even as it goes over the butte. However, it's a little bit difficult to see, but the arrows, as they go over the butte with the CFD solver, loop back in two different areas. And so we want to be able to try and bridge the gap between those two, to be able to capture these zones without having to solve those difficult equations. So two of the methods that were taken to kind of achieve the gold standard of the CFD solver is first the parameterization method, which is like just a straight mathematical approach to try and understand these cavity zones and use those in order to maybe better predict from the momentum solver where those may be. And then we also have a neural network method, which is a machine learning approach to predict from the mass conserving solver the output of the CFD solver. So there's great motivation for this problem because wildfires are able to cause a lot of damage. Recently, there was the Los Angeles fires that caused around $100 billion in damage, which is a lot. And 29 people or more lost their lives, and so many people lost their homes and businesses, and whole communities were destroyed. So if we are able to better predict the spread of wildfire, then we will be better able to prevent disasters such as this. So first we have this parameterization method. So this is inspired by research that was done by Kaplan and Dinar in 1996, where they were exploring how wind acts when it hits just a simple block obstacle like a building. And they worked to model this cavity zone here, which is our area of concern, through a variety of equations, inspired by the fact that this cavity zone is going to form an elliptical shape. And so the idea with this is, can we use this research to maybe apply it to more complex terrains rather than just a simple building? So the idea here is, if you have a complex terrain like a mountain or a butte, you can approximate it by a lot of smaller blocks, simple blocks like the buildings. And though it's not perfect, you can kind of capture the same idea. However, it's not perfect because you have to deal with the fact that if the wind hits, say, this block towards before the peak, the cavity zone isn't going to be directly after that. So you have to figure out a way to try and combine all of the cavity zones together and make sure you're able to pin where they are actually occurring. So this is an example of a natural terrain being approximated by these buildings or simple blocks. On the left, we have the actual elevation of the terrain, and then on the right, it's approximated by blocks of different elevations. The main idea is that if there are two points that are really close in height along the terrain, then we're going to group them into one building. So if you have a slight slant, then we can take that whole block and put it into one building. And this is very similar to like a Riemann sum integral or something along those lines. And so the results of that here is on the right, we have this prediction of where the cavity zones might actually be. And on the left, we have the CFD gold standard output. And we see the cavity zone is where the arrows are blue, right here. And on the right, it is able to capture a very similar shape. So that is very promising and indicative of the fact that the research done in the 90s can be expanded to more complex terrains. However, there's still work to be done, given that it is not entirely accurate. As we can see, there are some areas with maybe slightly lower elevation, but still enough to like make a difference, that are not being caught with these cavity zones. And so it's not perfect, but it is promising that there is room for more research there. The second method is this neural network method. The idea is to take the output from the faster math solver, and you use that, you put it through a neural network, and then it predicts the difference between the math solver and the CFD solver. And that way we can add that difference back into the math solver in order to get an approximation of the CFD solver. So kind of, yeah, a crash course in neural networks is you take a variety of input features, and then behind the scenes, there are you pass it through different layers in which parameters are learned that encode different information about the input features and how they may relate to the output features. And so in our case, we have things like the topography or the elevation of an area, what type of vegetation's in the area, the wind direction, things like that. And then we are trying to predict what the actual wind velocity field is. In this case, we are using a UNet convolutional neural network. And so it goes through layers that kind of reshape the data. And the reason for this choice is that it was originally designed for image segmentation and things like that. And so we very much care about preserving spatial features like we would an image. And so where things are in a grid is very important. And so that's why we use this style of neural network. So yeah, our inputs that were settled on for the neural network is a topography or an elevation file, as well as the mass conserving solver outputs. And those are both going to be grids that match the size of that represent the same size of an area of terrain. And then you take the output is going to be the difference between the solvers, and then we add that back into the math solver to get an approximation of the CFD solver. The Missoula Fire Lab was able to provide a lot of data for us. They have data from 201 locations with 16 different wind directions and 3 vegetation types, which gives over 9,000 different data points that we were able to use to train and test our neural network. And so in order to prep this data and use the neural network, we got data from the Missoula Fire Lab of the actual CFD solver output, as well as the mass conserving solver. And then we reduced the grid dimensions into 128 by 128. That was an arbitrary choice due to power of the computer and things like that. And some of the work that's currently being done is trying to expand the grid dimensions to maybe get more nuance in our predictions. But for now, we just reduced it to 128 by 128. And then we subtracted those two to get the true error between the solvers. And so we were able to train the model using the elevation and the mass solver, and then the true CFD solver in order to learn the weights within the neural network. So we set out a lot of data for testing. We made sure to not use the same location in the testing data and the training data, even if they had different vegetation, different wind directions and things like that, just because that can cause data leakage and can give us false positive results. So all the testing was done on completely different areas than what was trained on. And so we used 3 error metrics to kind of validate how well this model is doing. The first is the mean squared error, which is just a very classic metric used to determine the error between 2 things. The original is the actual mean squared error between the math solver and the CFD solver. And then there were 3 neural networks in this study, one that's smaller, meaning we have less layers in the U-net, and then a medium one and a large one. And we see that the mean squared error decreases greatly after applying the neural network to the math solver data. With the medium model and the large model being very similar. We see the same thing with the mean absolute error, and then the structural similarity index, which is just a common metric used to kind of see how similar two wind fields are. So there are some very promising results here. Structural similarity index is, of 0.77 is very high, as the highest you can get is 1. And then with the mean squared error and mean absolute error, we'd like those to be closer to 0, which are both achieved. They're closer than the original data is, so that is promising. So here's some images of the actual results. On the left, we have the actual difference between the math solver and the CFD solver, and on the right, we have the predicted difference using the neural network on the math solver. And as we can see, it gets a lot of the really important points that were missed with the math solver, such as these little like ridges, all sorts of ridges throughout the whole terrain that were missed. And then this is the same thing here, different vegetation. But yeah, the math solver missed, again, a lot of the nuances, and it was able to be picked up. And then this is an example of when we add the error back in. So on the left, we have the mass conserving solver output. In the middle, we have the CFD solver, the gold standard output. And then on the right, we have the predicted error added back to the math solver. And so visually, the neural network was able to get our results a lot closer than the mass conserving solver was. And then again, we see the same thing here. Not perfect, but certainly a lot better than the math solver alone. And then we wanted to explore some of how the errors vary across the different vegetation types. So we have grass, brush, and trees, which are all going to kind of affect how wind flows. And it appears that the neural network performs a lot better on the grass and the brush, which makes sense because trees are taller and are going to influence the wind more, so it's going to be harder to capture those, but it still is doing significantly better than the math solver alone. And then the other thing that we experimented across was different wind directions. And so along the x-axis, we have wind directions in degrees, and then the error metrics. And these are really validating to know that our model isn't just better at predicting one direction than another, because wind can flow in all sorts of ways, and we want to be able to capture the fire regardless. And then we look at the temporal complexity of each of the models, which is just the time that it takes to predict. And so on the x-axis, we have the test set size, so how many of those grids of terrain we're predicting the error for at a time. And the small model is very quick, as would be expected, and then the medium and the large are able to both predict over 1,000 different errors in a little over a minute. And it's worth noting that the medium model performed very similarly to the large model in error. And so the fact that the medium model is able to do so many in less than a minute is really impressive, especially since the CFD solver is a lot slower than that. So some of the conclusions from that, we have the parameterization method, and though not perfect and we haven't applied it yet, it provides a method for detecting cavity zones behind obstacles that are more than just a building, which gives evidence that the work of Kaplan and Dinar can be expanded in this setting for a more complex terrain. And then with the neural network, we were able to successfully employ a machine learning model that is able to balance how fast it is, the speed and the accuracy. So while not as accurate as the CFD solver, it is significantly more accurate than the math solver and significantly faster than the CFD solver. And so we hope to expand some of this work with the neural networks right now. I'm working on applying different maybe types of models in order to make these predictions more accurate while still maintaining the speed of the math solver and the current neural networks. But there are a lot of promising results that provide evidence that these things may be possible. So thank you very much. We have a lot of references. Specifically at the bottom, we have Jane's thesis that has a lot more information about this, as well as her GitHub that has a lot of this code. But yes, thank you so much.
Thank you. And I just, sorry to interject, I forgot two things I wanted to mention. On my slides, I named people in alphabetical order by last name. And then also I'm grateful to the students that provided slides, like Jane provided her thesis slides for the talk, and the other students, those pictures came from them.
Yeah, so any questions on that?
I do have one question, unless anybody else could ask. I could be last. It doesn't matter.
I have a question. Let's see. Well, both talks I really enjoyed. It's a good example of what applied mathematics can do, and data science in particular. What I was not always clear about is, are these computations and simulations time dependent, or do you assume a statistical average, or what is it? In Blake's talk, Blake, you had for example, the example of the Dixie Fire in California, where you try to determine the boundaries of the fire area. And I wasn't clear, is this after the fire, when everything has stopped burning, or is it during the fire, when the fire is still evolving? And the same question for you, Lydia. It wasn't always clear, so please help me out.
Yeah, with regard to the Dixie wildfire, so there it's a time-dependent model, but the fire had already burned. This was just used as a test case, but the goal would be to have accurate, faster than real life, to improve the models that are out there, to have accurate, faster than real life simulation of wildfire spread. And of course, in order to do that, wind is a very important feature of it. In fact, coupling the wind is important because wildfires create their own behavior. This year, there was an F2 tornado in southern Utah from a wildfire. Yeah, so it's important to capture that. So then with the wind modeling, it's not time dependent, but the idea is that you can use it every few time periods to update the wind flow.
Okay, yeah, that was my question, really. So is this averaged over some time interval, or is it a real prediction, not in real time, but so-called real time, right? Okay, well.
So basically a steady state for the Navier-Stokes. It's the Reynolds average Navier-Stokes they use. Yeah.
Right, I got it. Thank you. Thank you both.
Yeah, thank you. Yeah, and that's why the speed is so important, is because it is that just one moment in time, and so we want to be able to solve it real time.
Yes, got it.
So that's, if I could follow up, that's sort of a question I have about Wind Ninja. So is there a feedback from a fire, or it's really more about the topography at a high enough resolution to inform a fire model?
Yeah, the Wind Ninja is mostly, it's just looking directly at the wind and the wind flow itself, which can then be used to kind of use that later to model wildfires, if I'm correct, Dr. Barker.
Yeah, that sounds right. And it's also useful too, like even if you're just monitoring a fire, to know, for example, one of these main things that the math solver doesn't capture that the momentum solver does is when you have these eddies. And these eddies can be really important. For example, an eddy can like if you have the wind moving in a certain direction, but then there's an eddy that can move the fire in the opposite direction, that's an area that you need to watch. And so it helps wildfire fighters know areas or ridges that they need to watch during the night, for example, to make sure that there's not fire movement.
Okay.
Yeah.
And then I guess one thing that I might have just missed is, so for Wind Ninja, there's topography input, several inputs, I guess. But does it take like a boundary condition from a weather forecast or like a course grid set of winds to initialize from? Because it looks like it's fairly high resolution. Just wondering how that gets spun up.
Yeah, what ended up being settled on is the only inputs into the neural net are the topography, the elevation of the area, and then the output from the math solver. So it gives you that initial kind of guess of what the wind might be doing. But those are the only inputs. I know Jane tried a few other inputs, but they didn't influence results at all.
Okay, so if you, I guess if you had a prevailing wind like from east to west or north to south, that doesn't affect the output of this. It's more. Sorry, I'm probably just missing something.
Yeah, I think that would be inherently like found in the math solver
I see. Okay.
output, because that includes wind direction. So
Oh,
yeah.
okay, that's where it comes in. Okay,
Mhm.
awesome. Okay. I had a couple other questions. If no.
Yeah.
I just have one quick question.
Oh yeah, please go ahead.
Yeah, very nice talk. You mentioned the parameterization method, and I just wanted to know, because I know you said you didn't use it yet, but do you have some intuition on how would you use it?
That was mostly Jane's work in that part, so I don't know if I can speak on that. If Dr. Barker, you have more insight there.
Yeah, to clarify, this parameterization method is not the same as what's used oftentimes in computer-assisted proof, but it's a parameterization method in the sense that you identify structures and the way wind eddies form around those structures, based on this paper by Dinar and Kaplan, and so in their paper they've got buildings, and then you parameterize the eddy region behind it. So you come up with, say, a width and a length for the eddy based on the height of the building, the width of the building, the depth of the building. So the idea here was Jane was thinking of kind of like a Riemann sum idea. Like you take a mountain and you divide it into these skyscrapers, and then try to piece together what the eddies would look like based on this parameterization method of Kaplan and Dinar. So it was I think she had some really great ideas there. It did show some promise, but then it was somewhat abandoned because her neural network was doing so well. And then that, of course, is what Lydia's taken the ball and run with, because it seems to be the more promising of the two.
Thank you. Sounds good.
I just had a couple of questions about some of the data assimilation that was used for for the parameter estimation. I guess it was for the fuel types and fuel burn rates. This was what algorithm did you use for the parameters? So was this like an ensemble Kalman filter or?
Sorry, I think so you're referring to the wildfire modeling where there was data assimilation for determining the coefficients in the model for the different terrain types, the different fuel types,
Right.
right?
Mhm.
Yeah. So Drew used, so he had been working on looking at a bunch of different methods, including Bayesian methods,
Mhm.
but it was using Phoenix. And anyways, there were a bunch of challenges. And so in the end, he just used the Nelder-Mead algorithm to solve for the optimal coefficients.
Okay.
So that is one of the areas that would be interesting in the future, is to see if other data assimilation methods could give even better results.
Okay. Yeah. It's DA and fire is kind of tricky. Moves very
It,
quickly
and
yeah.
it can be really tricky to when you're working with different people's packages to get them to integrate. But
Right.
yeah, certainly we'd be interested in trying some of those other data assimilation methods.
Cool. Okay. And then I guess my last question is, at the beginning, you also mentioned studying the Dixie fire, and I think I just didn't catch what was the fire behavior model that was run.
Yeah, so this is a paper from 2008 that comes from there's a group of researchers, Mandel at the University of Colorado, Denver, and his group
Okay.
came up with this model. And it's basically, think like let's see, the heat equation, but then you've also got a ignition term, and then you have an ODE that represents the fuel, and these are coupled together.
Okay.
Yeah, and then it also accounts for loss to the air, the environment, things like that.
Yeah, the name sounded familiar, and I wondered if it was WRF S.F.I.R.E. that is this model that's been looked at UCAR in the past. But yeah, okay, cool.
Yeah.
It sounds
Yeah,
interesting.
it's a really nice model for if you want a PD model for wildfire that is complicated enough to capture behavior, but simple enough to work with. It's a really great model.
Awesome. Yeah, those are the best ones. Or some of the fun
Yeah.
ones.
Yeah.
To be able to run. Okay. Well, cool. Well, unless anybody else has any questions.
Maybe a last question.
Okay.
So I'm not familiar with it myself, but I've heard that Los Alamos has been working on similar type problems for a long time. Are you aware of that? Do you have any interaction with them?
Yeah, so Los Alamos definitely has been doing fabulous research for a long time. They have a really good, faithful wildfire spread model. One of the challenges with that model is that it runs on the Los Alamos supercomputers. And so for the wildfire fighters, it's not really practical. And then they have other things as well. There's I believe that we heard her talk, but I had the opportunity to do a little bit of support research for a project that was related to wildfire from a postdoc there. And yeah, I mean, that is kind of the challenge. Like, there are a lot of different wildfire models out there, both from various government agencies and private, and like these companies that do insurance, catastrophic modeling. So there are a lot of different models out there, but they're just, I mean, there's still a lot of room for improvement so that you can get a really accurate model that's also very quick and integrates data. So there's certainly plenty of opportunity for improvement in trying to find that optimal middle ground.
Okay, but at this point, there's no real, what shall I say, hierarchy of fire models that people in the real world accept or can use?
Well, so there's the Rothermel wildfire model back clear from the 70s, and I would describe it as sort of a model that captures the wave speed of the fire based on various inputs that have to do with things like the angle of the terrain, the type of input, things like that. So that's definitely been a very solid model for a long time, developed by the Forest Service. And then there are lots of other wildfire models that have come out and do quite well, honestly. Some of them are machine learning, some of them are based on PDs, some of them are a mix. I think that it's extremely challenging to model wind behavior, and that has a huge effect on wildfires. And I think that's one of the reasons why the Missoula Fire Lab is so interested in speeding up the computation and they're building and developing their model, because it plays such a huge role in modeling wildfire spread.
Okay, well, the more the better. At some point, the winner will come out, right?
Yeah, and maybe it's fair to say that like there are winners for different things that you're trying to emphasize. Like if you really want accuracy, or if you really want speed, or
Yes.
I mean, some of the challenges are then you get these wildfires that are moving at 100 miles an hour because of the Santa Ana winds or whatever, and yeah, or you get a tornado that's part of it, and anyways, it just really complicates things.
Sure.
Yeah.
Okay, well, thank you. Thank you both.
Thank you.
That was great. Tag team talk was very interesting. And so I got to find the clapping emoji, of course. So really thank our speakers. And other than that, if there's no more questions or anything else, I guess we will see you all next week.
Right. Sounds good. Thank you.
Okay,
Great.
thanks.
Thank you so much.